Hello. Welcome to a new virtual tour of the European Southern Observatory, or simply ESO. It's acronym. My name is Farid Char, and with the producer Hector Salas, we are going to be your guides during this trip to ESO Paranal Observatory. Okay. So just a little bit about me. I have more than 15 years of experience in astronomy outreach and education. I am one of the guides of the observatory since 2010. I am also part of the staff of an astronomy center in Antofagasta. And regarding my personal hobbies, I am interested in telescope observations and astrophotography. So, hello, Hector, how are you?
I'm Farid. How are you? Okay, so I'm going to introduce myself. My name is Hector Salas. I'm a PhD student in astrophysics at the Leibniz Institute for Astrophysics in Germany. My work mostly is related to the circumgalactic medium, that is the environment that surrounds galaxies, where there is a lot of gas and other things that interact with galaxies. And I've been part of the team that is the guides from Paranal since 2019. But since I'm no longer in Chile, I've been only been doing virtual tours for the last couple of years. So yeah. And as Farid said, I will be your producer today. And that means that I will be reading your comments, your questions, and during the tour we'll have a couple of spaces for us to answer them. So please write your comments either in YouTube or in Facebook. And I hope you enjoy the tour. So Farid, you can continue.
Yeah, thank you, Hector. So, okay, well, ESO wants to, of course, to be with you during these virtual visits and bring astronomy directly to your home or wherever you are. So please remember you can send your questions and comments during all this streaming. And you can imagine you already have several questions. So to do that, you can leave your comments or questions in the comment section of this broadcast. You can say your name and city, so later we can announce it during this tour. So Hector will be waiting for all your questions. So regardless of where you are now, Chile, South America, Europe, we are going to be very happy to answer all your questions. And also, please don't forget to share this experience in case you like it with the share buttons on Facebook or YouTube. So, okay, now we are going to start with this tour. We want to help you to understand the place of our visit. Okay, so we will begin with some information about the European Southern Observatory, or ESO. So ESO is composed by 16 member states. Okay, so I think we have an image. Yeah, we have the image of the member states of ESO. So the headquarters of ESO are located in Germany. Also, Australia has recently joined ESO as a strategic partner. Okay, so this is the main structure. Chile is the host state and home of all ESO observatories. So from the 60s, and with those objectives in mind, ESO has chosen one of the best places on the planet for astronomical observations, the Atacama Desert in Chile. So during this period, Chile started several site explorations in order to attract international observatories, such as ESO, to our country. As a result, Chile offered its territory and ESO did choose the more suitable areas. So the mission of ESO is to design, build, and operate astronomical observatories. Okay, why? To enable important scientific discoveries and incentivize the promotion and cooperation in the astronomy field. So right now, you will see a picture with the three main observation sites of ESO in Chile. Okay, we have the sites here. So in first place, we have the Chajnantor Plateau, site of the ALMA and APEX radio telescopes. ESO is part of these places for radio astronomy alongside other international partners. So additionally, south of Atacama Desert at 2,400 meters, we have La Silla Observatory in the Coquimbo region in Chile. Okay, so this observatory is the home of several telescopes, such as the NTT or the 3.6-meter ESO telescope, and this one is using the HARPS instrument. And the HARPS instrument is something like an exoplanet hunter. Finally, we have the place of our visit, Paranal Observatory. So this ESO Observatory is the home of the Very Large Telescope, or VLT, the most advanced visible light telescope on the planet. So in the next few years, we will also have the Extremely Large Telescope, or ELT, the biggest visible light telescope on Earth. Also, the CTA will be an array of telescopes focused on capturing gamma rays. Okay, now we have a better picture. So now let's travel to the Paranal Observatory. We are going to show you a simulation. Okay, now we have the simulation. So virtually you are flying over the Atacama Desert in the north of Chile, about 1,600 kilometers north of the capital, Santiago. Specifically, about 130 kilometers south of Antofagasta, the regional capital, and about 90 kilometers north of Taltal, the closest city. So now we are going toward the mountain top of Cerro Paranal, located at 2,600 meters above sea level. This mountain belongs to the coastal range, and despite its altitude, it is located at just 12 kilometers from the coast. And where's the bush? Where's the ocean? The Pacific Ocean is located below this cloud cover you see in the horizon. So why those clouds if right here the sky is so clear, dry, and lonely? Well, this is because of the influence of the Humboldt current. This is a cold current near the coast of Chile and Peru, cooling the atmosphere and causing a phenomenon called thermal inversion, and at about 1,000 meters above sea level, keeping below the cold, humid, and basically bad air for astronomy. So about the layer instead, we have the hot, dry, and less dense air. So this is something like the good air for astronomy. So the clouds are blocked by the coastal range, and near Paranal, the mountains are high enough, surpassing 2,000 meters above sea level. So what other natural barriers we can expect in this area? So, well, about 200 kilometers to the east, we have the Cordillera de los Andes with very high mountains, more than 6,000 meters above sea level. So, this is another natural barrier against blocking clouds from Argentina and Bolivia in this case. So, the main result is this landscape, a place with an average of more than 300 clear nights per year, with a very clear and transparent atmosphere, making it ideal for observing the night sky. Also, here we are far away from artificial light sources because of human activity, I mean light pollution. So this is one of the best places on Earth for astronomical observations. Okay, okay. So right now we will change the view to have an even closer look to Paranal. Okay, here we have this additional view. So as you can see, this is not an ordinary mountain, and now we can see the different telescopes and structures in this mountain. We are at the summit of Cerro Paranal. So do you know what Paranal means? Well, in the Quechua language, Paranal means whirlwind, possibly because of some whirlwinds forming in the desert. However, as I told you already, the atmosphere here is extremely quiet, so this observatory is a true oasis. So you will see how in one of the driest deserts we have a lot of life and a lot of science. Okay, so right now we will visit the summit of Paranal. Okay, so now we have the summit, as you can see here. So in front of us, we have the Very Large Telescope, or VLT. It's an acronym. So if you see the amount of buildings, I mean 4 giant domes and other four small and rounded ones, it is clear that the Very Large Telescope, in fact, is not only one, but a very special array of telescopes. So all this facility is the most advanced optical observatory on Earth. So let's take a closer look. So here you can find the 4 unit telescopes, or UTs. Okay, here we have UT1, UT2, UT3, and UT4. So in this case, um, each telescope has a primary mirror of 8.2 meters in diameter. So these are the giant ones in your screens. And the other small ones are the auxiliary telescopes, or ATs, each one with a primary mirror of 1.8 meters diameter. So in this case, I am talking about this one, this one, this one here, and we have one last one here. So those ones are the auxiliary telescopes, and the big ones here are the UTs. Okay, so they are the main telescopes in this complex. So each UT, each telescope, one of the big ones, has a name in Mapudungun. This is the language of the Mapuche culture, the natives from central south of Chile. So here we have Antu, and Antu means sun in Mapuche. This one is Cuyen, and Cuyen means moon. This one is Melipal. Melipal means 4 stars, but this is a reference to the Southern Cross constellation. And this one is Jepun, and this is a reference to the planet Venus. Okay, so basically, all the telescopes, they have, let's say, astronomical names. Um, Now, these small telescopes, as I told you already, are the auxiliary telescopes. Okay, so regarding the small ones here, they are very special because in the case of the small ones, they are mobile and they can be moved using a rail system uh, up to 30 different positions. So they were specifically designed to work all together as a single big telescope with a variable diameter, able to reach up to 200 meters, as you will see in a few moments in a short video. Okay, so here we have the video. This technique to combine light from several telescopes is called interferometry. Okay, so we are able to observe much more specific details if you compare this with the individual telescopes. So thanks to interferometry, we can simulate a giant mirror to distinguish details up to 16 times fainter than a single telescope. So why don't we make small telescopes and combine them to create a huge telescope? Well, interferometry also has limits, and some information is lost during its travel. However, it is still an excellent solution to observe objects too difficult to observe with our current technology. Okay, so right now we are going to come back to the tour screen. Okay, so now we are present here again in the main platform, and now we are going to have the opportunity to visit one of the telescopes. We are going to enter specifically to this one, to Melipal. Okay, so in order to do this, well, I think it's important to mention that we can't enter to all the telescopes, but don't worry about that because the 4 ones are identical in size and shape. So the only difference are the instruments inside. So you can know more about the instruments on the ESO website, of course. Okay? So now we are going to enter to the UT3 telescope. Okay, so here we have this telescope. We are now inside of the UT3. Okay, so when you see this telescope, when you see this big telescope, the first thing you can realize is that it's a very big telescope. It's a giant telescope. So we are right now on the last floor of this telescope at the same height of the main mirror in front of us. So the mirror has 22 tons with 8.2 meters in diameter and only 17 centimeters of thickness, created from a ceramic and flexible material called Observatory. So here we have the mirror, and I am going to do a close-up so you can observe better this structure of the mirror. So as I told you already, the material of the mirror is a ceramic and flexible material called Observatory. So how can we point the telescope to the sky without breaking it? So we can see this telescope from another angle in order to explain that. So now I will show you, well, as I told you before, this is the last floor of the telescope, but now I can show you something from this level, from the ground level. Okay, so now we are in a different position. We are in the ground level. So from this position, I can explain that the mirror is mounted over this white structure here. Okay, so all the telescope, sorry, all the mirror is supported by this white cell. Okay, so this is a cell supporting all systems assisting the mirror, including something called active optics. And here you can see some little gray boxes. This one here, this one, this one, this one. So you can see many gray boxes there, and they are very important in this system because the gray boxes there are something called actuators. They are a kind of piston, and we have 150 in total, controlled by a computer. So they are acting on the mirror during the observations in order to keep the optimal shape of the concave mirror, because this is a concave mirror. Okay, so the actuators are basically preserving the same concave shape of the mirror because if we don't do that, it could suffer deformations just because of gravity physics. So those deformations, imperceptible in a first view, could be critical in the result of the observations. So that's why we need those actuators. So how is this working together? We are going to come back to the last floor to explain that. So I will return to this view right here. Okay. Okay. So now we can we can explain this let's say procedure of how the light is going to the telescope by using a short simulation. So Hector, do we have the simulation? Okay, thank you. So this is what happens. The light is entering to the telescope, so we have to open the dome, of course. And when the light is going to the telescope, the light is going to impact in the primary mirror, will be concentrated and reflected to the secondary mirror, and will be reflected again to a tertiary mirror. So this tertiary mirror will reflect the final picture to one of the instruments, and we have three instruments. You can see the instruments there in different colors. So each instrument is different. Okay, so we are trying to use different instruments because the instruments are doing different things. So this simulation, as you saw before, is basically explaining how the instruments are receiving the light. Okay? Because we have basically three mirrors: primary, secondary, and tertiary. and the tertiary mirror is able to rotate or or or, or adjust the inclination in order to reflect the light to the different instrument we are using in every time. So in this case, each UT has three instruments. Okay, in this case, Melipal has two at both sides and one underneath the mirror cell. So in this case, you can see one of the instruments here. The other instrument is in the other side, it's not visible here. And here, underneath, we have the other instrument. Okay, so this is more or less the same you saw in the simulation before. Okay, so this is basically how the telescope is catching light. This is basically how the telescope is sending the light to the instruments, and the instruments, of course, they will convert the physical light into a digital image, a digital picture. So the astronomers will be in control room to take a look to those pictures. Okay, so basically, all this digital picture is sent by optical fiber. Okay, to a computer in order to be analyzed. So this is of course a very modern system, and and this is how the astronomers are working in a professional facility like this one. Okay, so in this way we finish now our visit to the telescope. Okay, so this is and this those people here are basically engineers. They are doing maintenance. They are doing some kind of uh, let's say fixing problems, preparing the telescope for the next observation night. So that's why we have engineers working here during the day. But okay, so now we are going to return to the platform. We are going to the platform again, and the next step will be to continue with the control room. This is the workplace for astronomers and scientists performing the observations. The control building is located not in this platform, but let's say just next to the platform here. And we are going to visit this place in a few moments. Okay, but before going to this area, before going to the control building, maybe it's time to take a look if we have some questions. So, Hector, do we have some questions so far?
Okay, Farid, we have a few greetings from Amsterdam, from Peru. Uh, we have so far only one question from Paweł Lech. I hope I pronounced it right. He's greeting us from Poland, and he's asking us about the most distant galaxy found with the BLT. Do you know something about that, Farid?
Well, this is a tricky question because this kind of, let's say, records is changing all the time. As far as I know, this I don't remember the exact name of the galaxy, but it was so distant. It was only 600 millions, yeah, 600 million years old, and I don't know if you can explain better this, but it has a redshift of 8.6, so something like that. So this is the most distant remote galaxy so far, and basically it was like a baby. I mean, when the universe was something like a baby, because 600 millions years old is a very short in terms of the old the old age of the
Okay.
universe, right?
Yes. So put it in perspective, the age of the universe is uh, 1,300 millions, no, 30,000 millions years. So it was
Yes,
just 600 millions. And okay, you mentioned the redshift,
exactly.
so maybe let's try to explain that a little bit. So The redshift has to do with the spectrum of light, so how it moves when things get away from each other. But to put it just very simply, the higher the redshift, the farther away something is. But this is not linear. A redshift of 4 is not twice as far away as a redshift of 2. This is sort of like exponential in a way. So something that is a redshift 10 is very far away. Something which is close to the beginning of the universe, for let's say. And
Exactly. Yes.
yeah, yeah. So it's kind of complicated to transform this into distances that are more understandable, let's say, or more easy to grasp. Okay, we don't have more questions, but maybe I could ask you one of the usual questions that people have when they visit in person. Okay, so you have mirrors. Do you need to clean them, or do you need to do some kind of maintenance to those mirrors?
Yeah, sure. In order to explain that, we can come back very shortly to the Millipar telescope. So yeah, as you can see the mirror, for example, when you see the mirror here, maybe you can notice that the mirror looks very clean, looks very nice, looks in optimal shape because yeah, we have to do some kind of cleaning, and we have two ways to clean the mirror. One way is something like an easy way because we have to we need only maybe a couple of engineers to do that. And in this case, we have to use something like carbon dioxide snow. Okay, so this is something like a foam. So we have to basically rotate the mirror a little bit, and one of the engineers, this person is going to spread this kind of foam, carbon dioxide, in order to remove dust, because we are in the desert, we have dust. So we need to do this something like only once a month. So we need to spread this carbon dioxide foam, and because the mirror is tilted, the carbon dioxide and the dust is they are going to fall to the ground, okay, by gravity. So this is a simple process to remove dust from the mirror, and we need to do this only once a month. And the other way to clean the mirror is a little bit more complex, and we need to do this every 18 months, so 1 year and a half. And for this process, we need to remove all the mirror from this building. So basically, uh, we need to remove this mirror, but also the white cell. Okay? So we need to use some special cranes to do that. So we need to open something like a door located here, and we need to extract the mirror, and we need to uh, put the mirror in a special vehicle outside, and this special vehicle is going to transfer the mirror down to the base camp. And in the base camp, we have a special facility to do something with a process we call recoating. Okay, the recoating is something very special because this mirror, when I was explaining the specs, the facts about this mirror, well, the surface of the mirror is made of a very thin layer of aluminum. So the recoating means that we have to remove this aluminum layer, and we have to put a new one. Okay, so we have to remove the old aluminum with some chemicals, and we have to put a new layer of aluminum, and this layer is very very thin. It's something like 80 nanometers. So if you think about this, it's almost like change the mirror, because you are changing the reflective surface, the reflective layer. So once the mirror is ready, we have to put the mirror again in the vehicle. The vehicle is coming again to the platform. So we have to lift the mirror, and we have to reinstall the mirror in this telescope. So the mirror and the telescope will be ready again for observations. So that's why how we are doing the cleaning of the mirror.
Okay, thank you for it. Um, I think we can continue with the tour, and please to the people watching, if you have some more questions, write it in the comments, and we have a second pause for answer them at the end of the tour.
Yeah, sure. Thank you, Hector. So we are going to continue now. We can now visit the control building. So the control building is this facility here. So now you can see the control building from the opposite location. As you can see, it's a separate facility, independent from the telescopes, and it's located in a different, let's say, level of the mountaintop. The astronomers are working specifically here in the last floor. So now we are going to visit this area. Okay. Okay. So now we are in the control room, and from this position you can see some very important things. So in this case, we have a lot of workstations. Okay. So this workstation right here, for example, is only dedicated to this telescope, Melipal. So all operations with Melipal are from here. Okay, so you can see a lot of computers, a lot of uh, say monitors here, but this workstation is specifically for that telescope. In the opposite side, we have another workstation, in this case for Jepun UT4. Okay, so now if we continue working virtually here, I can show you that we have different workstations, in this case for UT1 and 2. Okay, and in the other side we have the workstation for UT2 Guyen. Okay, so basically this is where the magic happens. This is the place with workstations for each telescope. So all the telescopes, instruments, and systems explained before are controlled from here. So during the day, engineers, technicians, and scientists are working to prepare the telescopes for the next observation night. Let's take a closer look to this workstation. Okay, so um, each night we have a telescope operator and an astronomer per telescope in order to do the observations. For example, here you can see a couple of people. We have this person here, this person here. So they are working in this workstation. So let's say that the telescope operator is in charge of technical details and the movement of the telescope. So the telescope operator is someone like the pilot of the machine of the telescope, and the astronomer, the ESO astronomer, is in charge to direct the scientific observations, and this person will decide the next steps. So the astronomer is someone like the co-pilot. Okay, so the observations are performed by experts from ESO for scientists from all the planet. Okay, so this is basically how the people is working here. As you can see, is only a lot of computers, a lot of tables here. Is nothing so extraordinary, but of course it's very important because from this place is where the astronomers are working and making a lot of discoveries. Okay? So I don't know, Hector, if do we have additional questions to answer at this point?
Okay, we have a question about the lasers that you sometimes see in pictures of in videos about from Paranal Observatory. So, what
Yes,
are those lasers? Can you tell us something about that?
yes. maybe I can. I don't know if it's visible from here, but oh yeah, maybe I can. Yeah, yeah, maybe I can point to this picture. I don't know if it's possible to see, to take a look here. Yeah, this is the laser. Um, the laser is installed in only one of the telescopes. It's only in the Jepun telescope in UT4. Basically, the laser is a way to assist a technology. One of our technologies we are using in Paranal, and this technology is called adaptive optics. So, um, to give a simple explanation, the adaptive optics system is a way to compensate the atmospheric turbulence. Uh, well, we are all well, on the Earth surface, but above us we have the atmosphere. So the atmosphere is a mass of gases moving. So in order to observe the stars, when you are looking to the stars, the, the light from the stars is not reaching your eyes in a straight line exactly. Okay, in the vacuum of the space, yeah, the light from the stars is traveling in a straight line. But when this light is crossing the atmosphere, becomes turbulent because the atmosphere, as I told you already, is a mass of gases moving. So this light is traveling like that in a distorted way. So that's why when you are looking at the stars looks like blinking, okay, because of this atmospheric distortion. So in order to correct this problem from an observatory like Paranal, we are using a very interesting system in the telescope, including a deformable mirror to correct this distorted light in order to compensate the distortion and to get some kind of correct reflection of this light. But in order to assist this technology, adaptive optics, this laser is basically creating an artificial star in the sky. Because sometimes when we are observing the star, the universe, sometimes we need to use a reference star or a guide star. And sometimes in the field of view of the telescope, we don't have any star as a reference, so we have to create one. So in this case, this laser is creating an artificial star because this laser has a very long range, something like 90 kilometers. So at this altitude, the laser can excite the sodium atoms of the high atmosphere, and we can basically create this artificial star, and this artificial star will look, yeah, we can take a look at how distorted it is this artificial star. So we can calibrate our adaptive optics system in order to analyze how to correct the picture. Okay, just for your reference, this picture is showing the old laser system because the current laser system has four beams. Okay, so we have four laser beams in the UT4 telescope because this new system is more accurate actually. In order to do this, to correct or to yeah to assist the technology of called adaptive optics.
Okay, thank you for it. A question from me, since I don't see more from the audience. Maybe you can tell us a bit about who can use these telescopes. Like, does any astronomer from any country can use them, or and if they want to use them, what do they have to do?
Yeah, well, the first thing is that even if we have some kind of open skies policy, like any institution can apply, we have a system where people need to submit a proposal. So we have 2 times during the year, in April and October, we have a call for proposals. So institutions, astronomers belonging to some institutions, okay, they can apply for telescope time, and we have to select the best projects. Of course, I mean, we cannot allow everyone to observe because we don't have enough telescope time. So we have to select the best project, and usually we are receiving 5 times more proposals than we can approve. So basically, in this context, we have a scientific council in charge to evaluate these proposals, and after the proposal is approved, if the proposal is approved, the astronomer requesting this telescope time will get some telescope time, and in this case, the telescope time depends on the requirements of the investigation. So sometimes maybe you need 2 hours of telescope time during, I don't know, 3, 4 nights. Sometimes you need only half an hour for one single night or 2 nights. So it depends. That once you have the telescope time, well, we have a system where you can come to Paranal physically, and this is something called visitor mode. And we have another system called the service mode. And in service mode, you don't need to travel to Chile, to Paranal, because one of the ESO astronomers can take care of your observation. But basically, and in order to answer the question, yeah, we have some kind of policy where any institution can apply, but under certain circumstances, if you have two projects and one of the projects is from an ESO member state, they probably will get some preference in terms of if the science is enough, if equally good. Okay? But yeah, you have to consider that we have to filter and select the best projects. That's the main criteria, the scientific criteria.
Thank you very much, Farid, for your answers. And we can continue the tour for now.
Yeah, sure. Okay, so this is the end of the explanation of the control building. So now we can return to the main platform. So give me a moment. Okay, so now we are in the platform again, and now you have a lot more information about the observatory and the people working here. Now I want to invite you to know more about the main scientific milestones made from all ESO observatories. I mean, La Silla, Paranal, and Chajnantor. So scientific staff from different countries are using the ESO telescopes to study objects near to our home solar system, and also others located in the more distant places in our universe. Okay, so observations with the ESO telescopes have been very important, okay, of course. And now we are going to explore a list of the top 10 discoveries from ESO sites so far. So please, Hector, we can take a look to the list.
Observations with ESO telescopes have led to many breakthroughs in astronomy, and over the years have been responsible for some truly remarkable findings. Here is our list of ESO's top 10 astronomical discoveries so far. Astronomers using ESO's Very Large Telescope have discovered by far the brightest galaxy yet found in the early universe, and found strong evidence that examples of the first generation of stars lurk within it, stars that were previously only theoretical. These massive, brilliant objects were the creators of the first heavy elements in history, elements that are necessary to forge the stars we see around us today, the planets that orbit them, and life as we know it. ESO telescopes have provided definitive proof that long gamma-ray bursts are linked with the climatic explosions of massive stars, therefore solving an enduring mystery. A telescope at La Silla was also able to observe the visible light from a short gamma-ray burst for the first time, showing that this family of objects most likely originates from colliding neutron stars. Astronomers using ESO's HARPS instrument in 2010 discovered a planetary system containing at least 5 planets orbiting the Sun-like star HD 10180. They also found evidence that 2 other planets may be present, one of which, if confirmed, would be among the lowest mass exoplanets ever found. Newer observations and reanalysis of the data suggest that there could be even more planets around this star. ESO's Very Large Telescope was used to detect carbon monoxide molecules in a remote galaxy, seen as it was 11 billion years ago, a feat that had remained elusive for 25 years. This allowed astronomers to obtain the most precise measurement of the cosmic temperature at such a remote epoch, and it matched the temperature predicted by the Big Bang theory. The atmosphere around a super-Earth exoplanet was analysed for the first time using the VLT. The planet, which is known as GJ1214b, was studied as it passed in front of its parent star, and some of the starlight filtered through the planet's atmosphere. The atmosphere was found to be either mostly water in the form of steam or dominated by thick clouds or haze. Using ESO's VLT, astronomers measured the age of the oldest star known in the Milky Way. At 13.2 billion years old, the star was born in the earliest era of star formation in the universe. Uranium was also detected in a Milky Way star and used as an independent estimate of the age of the galaxy. The VLT obtained the first ever image of a planet outside our solar system. The planet, which has a mass about 5 times that of Jupiter, orbits a failed star, a brown dwarf, at a distance of 55 times the average distance between the Earth and the Sun. In 2014, ALMA, the Atacama Large Millimeter Submillimeter Array, revealed remarkable details of a solar system that is forming. The images of HL Tauri were the sharpest ever made at sub-millimeter wavelengths. They show how forming planets are vacuuming up dust and gas in a protoplanetary disk. One of ESO's proudest moments came when 2 independent research teams, including ESO staff, arrived at a truly revolutionary finding: that the cosmos is not only expanding, but that it is doing so at an increasing rate. The findings of the separate teams were based on observations of exploding stars, or supernovae, including measurements made from ESO's telescopes at La Silla and Paranal. This discovery was rewarded with the 2011 Nobel Prize in Physics. And finally, several of ESO's flagship telescopes were used in a 20-year study to obtain the most detailed view ever of the surroundings of the monster lurking at the heart of our galaxy, a supermassive black hole. Astronomy is always moving forwards, and ESO's top 10 scientific discoveries are not set in stone.
Okay, so this was the top 10. I hope you enjoyed. We have just one more thing. So we have something like a bonus track. So let's take a look at this now. This is some video related to a black hole. So a team of astronomers was able to capture the first image of a black hole some time ago, thanks to the Event Horizon Telescope. or EHT for its acronym. This was an array of 8 ground-based telescopes distributed on the planet, working as an international collaboration, and it was able to achieve the first direct evidence of a supermassive black hole, as you can see from this simulation. So the picture reveals the black hole in the center of Messier 87. This is a massive galaxy in the close galaxy cluster in the Virgo constellation. This object is located 55 million of light years from Earth, and its mass is about 6,500 million times the mass of our Sun. Okay, so we hope you liked the top 10. This was only a fraction of the discoveries thanks to the ESO telescopes and the scientific stuff behind them. Okay, so now we can continue, and from the platform again, we are going to do a very special activity thanks to this virtual tour. We are going to observe the night sky from Paranal. So we are going to change this perspective to show you a little bit of how the night sky looks like from this observatory. Okay, so now you are looking at night sky. As you can see, the sky is almost completely dark. Okay, with the last traces of light from the twilight. So the moon is below the horizon and the sky is full of stars. So here we can see the first interesting thing. We can see a very popular constellation. We are looking at the Orion constellation right here. So I am going to do a close-up in order to show you this, this area of the sky. So this constellation represents a hunter. You can recognize it with those 3 stars somewhat aligned, and these stars are representing Orion's belt. And inside of Orion, we can see another interesting object. We can see the Great Orion's Nebula here. Okay, so this is a very interesting object to observe. So now we are going to change the position and move to the brightest star of the night sky. And this star is called Sirius. So here we have Sirius right here. Okay, so Sirius is a star belonging to the Canis Major constellation, and it's representing Orion's hunting dog. Okay, a little bit down next to Antu, the Antu telescope, okay, I will show you. We can see another interesting object just right here. We can see an open cluster of stars, and this one in particular is the Pleiades. Okay, so this is an open star cluster located in Taurus constellation. So the majority of those objects are visually close to a specific area, a very populated area with a lot of stars. So actually we are looking at one of the Milky Way arms, our galaxy, and our sun is only one among hundreds of millions of stars. Okay, so if you look carefully, you can see that this area has a lot more stars if you compare with this one or this one. So this is one of the arms of the Milky Way. Okay, so during the winter in the southern hemisphere, we can see the center of the Milky Way, and this is another area full of stars between the Scorpius and Sagittarius constellation, and you can see all this area from this hemisphere. Okay, so now we are going to move to another sector in the sky to find 2 spots in the night sky. So I am going to rotate the view, and now we have those spots right here. Okay, so those spots are something very interesting here. These are the Magellanic Clouds. So up there is the large Magellanic Cloud, and down there is the small Magellanic Cloud. And they are not actually clouds, of course. They are galaxies with an irregular shape, both visible to the naked eye in a clear night like this one. So the name refers to the records Ferdinand Magellan during its circumnavigation of the planet in the 16th century. So during this time, the people were unaware about what a galaxy is. So another important area right here is the smallest constellation of the sky, the Southern Cross, this one right here, this one. So regarding the Southern Cross, the cross is tilted now, and this is an easy constellation to find the sky, only visible in this hemisphere, and a good guide to find the South Celestial Pole. And this is a projection of the Earth's south pole. So during the night, the stars appear to revolve around this point. So to find this point, we are doing this. We have to extend the, let's say that the longer stick of the Southern Cross right here 4.5 times. So we have to do 1, 2, 3, 4.5. So more or less like right here, we have the South Celestial Pole. So this area also indicates the South Cardinal Point. So basically, if we look at the horizon right here, you are looking to the South Cardinal Point. Okay, sorry. So this is the conclusion of the visit to Cerro Paranal. So now we are returning to the platform in daytime to show you the last part of this activity. We are going down now to 2,400 meters to take a look at a very specific place in the base camp. This is the base camp, okay? And in this area, we are going to visit specifically one facility here, and this facility is called the Residencia, okay, or the residence. So this is the residence. So what happens here? The residence is basically the place where the ESO staff can stay and rest. So the residence is the home of the ESO staff during their work in the desert. So let's enter now. We are going to enter right here. And here we have the residence. Residence is very beautiful. It's a very beautiful place. And here the workers can enjoy a more humid air. So they have a swimming pool, green areas, and also some rest if you compare to the desert and the intense sunlight from the outside. Okay, so this is the last part of this visit. So I think during this time in the residence, Hector, we can check if we have one last question in order to finish this tour.
Okay, we don't have any more questions. We have more greetings from Bremen in Germany, from Costa Rica, from Romania, from Lebanon, from Australia, Nicaragua, Nigeria, Honduras, a lot of places. People are watching us from all over the world. I would like to take the opportunity to tell people that in addition to the spiritual tours that we have every week, we have in Spanish and English for Paranal Observatory and also Spanish and English for the Sea Observatory, but we also have in-person tours. So maybe you can tell us something a bit about those, Farid?
Yeah, sure. We have visits to Paranal Observatory every Saturday in two blocks, morning tour and afternoon tour. The morning tour is at 10 a.m. and the afternoon tour is at 2 p.m. So you have to book in advance. You have to do it online on the ESO website. I recommend to do it in advance because we have a lot of people going to the observatory. And yeah, you can enjoy in person and take a look of all the facilities with the assistance to one of the tourist guides.
Yeah, and this is completely free. You don't have to pay anything for it.
Yeah, exactly. It's completely free. So the only thing you need to take care of your own transportation. but there is no entrance fee. You can go and enter for free. And the tour in person takes something like 2 hours and a half. So we invite you to everyone to take a look and visit Paranal Observatory in person because of course it's a very nice experience.
Mhm.
Um, yeah.
Yeah,
Okay, Hector,
I
I think
was.
we are ready to
Yeah, we
finish.
are ready to say goodbye. It was my pleasure to be here and be part of this tour today. Please let your friends or anybody that you know that might be interested in astronomy or science that we are doing these spiritual tours. And I hope to see you maybe on a next occasion.
Yeah, sure. So we remind you that this visit information and pictures are available on the ESO website, and this is and in this way we are finishing our tour today. We have a survey to receive your comments about this tour. So the link to this survey will appear in the comment section. So I hope you like this virtual experience. Please stay alert to the ESO social networks to know when we will have our next tour. So on behalf of ESO, I want to say thank you very much for your presence. So goodbye.
Goodbye.